Hello everyone, welcome back. My name is Mr. Kovalt, and in this video I'm going to be going over another example where we use the Henderson-Hasslebach equation, but this time we're going to use it for a simple basic buffer and we're going to have a dilution. So let's get into this. Okay, so here's the problem. We have a solution is made by mixing 200 milliliters of 0.30 molar ammonia and 300 milliliters of 0.25 molar ammonium nitrate. What is the final pH of the solution? So a couple of things we need to notice here is that this is a buffer solution, so check, that's one of the criterion, is that we need to have a buffer solution if we're going to use the Henderson-Hasslebach equation. So the base and the conjugate acid are present in fairly high concentrations even after dilution. Yes, we do have to do a dilution because notice that we're mixing 200 milliliters of one solution with 300 milliliters of the other solution. And of course, when you mix them together, the volume changes and therefore the molarity of all of the species in the mixture is going to change as well. So we need to recalculate those molarities. So once we mix these together, these molarities are not going to be the same, they change. So we'll have to calculate those. The nitrate ion is a neutral spectator ion. It is maybe slightly basic, but we can ignore that ion. It's basically a neutral ion. Okay, so we need to do that molarity calculation or that dilution calculation. So just remind ourselves that the molarity or the dilution equation is M1V1 equals M2V2. In this case, the M1V1 is our starting molarities and volume. So we're going to start with that. And then M2 is the new molarity and the V2 is the new volume. At this point, when you're mixing them together, the new volume is going to be the total volume of the two substances mixed together, assuming that the volumes are additive. And so therefore, we would add 200 milliliters to 300 milliliters, and that's going to give us 500 milliliters total. So when we set up our equation, we solve for the new molarity. That's going to be equal to the old M1V1, the starting molarity and volume, divided by the new volume, which is the total volume. So when we plug in the values for the molarity of NH3, we have 200 milliliters multiplied by 0.30 molar to start with. We divide by the total volume we end with when we mix them together, which is 500, and we get a new molarity of the ammonia at 0.120 molar. The 0 is added to avoid rounding errors, but again, we are limited to 2 sig figs here. Okay, so for the ammonium ion, the conjugate acid of the weak base, we do the same calculation. So here we start with the V1, the initial volume of the ammonium, which was 300 milliliters. And then we multiply that by the initial concentration, which was 0.25 molar. And then we divide by the total volume again, which is 500, and we get 0.150 molar. So this is the new calculated volume after mixing. So now that we have these concentrations, we can see that they are still fairly large, and we have a good amount of both of them together in solution. So it's a good buffer system. So the next thing we need to do is look at the Kb value for the base. And so to look that up, we can calculate that as well. So stay tuned. Okay, we're back, and I think I had just misspoke about Ka and Kb. So we need to find the Ka value when we use the Henderson-Hasslebach equation, so because that includes the Ka value. However, we can find the Kb value by looking it up. We can't find the Ka value for ammonium because it's just not tabulated. It's the conjugate base, the conjugate acid of weak base, and the conjugates are not really found in tables, but the base is. So the weak base is ammonia, and we can look that up. So the Kb is equal to 1.8 times 10 to the negative 5 for the ammonia. And so we can use this equation, the Kw is equal to the Ka of the acid multiplied by Kb of the base. These are conjugate acid-base pair. So you multiply the Ka and the Kb together, you get Kw. So since we can look up the Kb, we can solve the equation for Ka. So Ka is equal to Kw over Kb. We plug in Kw, which everyone should know is 1.0 times 10 to the negative 14, divided by the Kb, 1.8 times 10 to the negative 5. Oops, that should be negative 5. Sorry. And so from there, we get 5.55 times 10 to the negative 10. So now we got the calculated Ka value, and you'll notice right away that this Ka value is very, very small compared to the concentration. So the concentrations were 0.120 molar and 0.150 molar from before, so much, much smaller than they. So therefore, the conditions are met in order to use the Henderson-Hasslebach equation. So we have a buffer, and the Ka value is significantly small. Therefore, we can assume or suppose that the X is going to be negligible, that change is going to be negligible. And so now we can just plug everything into our Henderson-Hasslebach equation. So we have our Henderson-Hasslebach equation right here. The pH is equal to the pKa plus the log of the concentration of base over the acid. So we plug in our newly calculated Ka value, so 5.55 times 10 to the negative 10. By the way, if we calculate this, we get pKa is equal to 9.25. We add the log of the base over the acids. So when you add this together with this, you'll see that we got a 9.158 value. And so I want to point out that the pKa is 9.25, but the pH we calculated is 9.158, which is lower than the pKa. The reason for that is because if you look at the ratio here, this is the concentration of the base, this is the concentration of the acid, the conjugate acid, ammonium. You'll see that the acid is more concentrated than the base. We have more acid in solution, so therefore it's going to affect the pH by bringing it down compared to the pKa. So if you take the log of this ratio is less than 1, you take the log of a ratio less than 1, you end up getting a negative number, and so we subtract from the pKa, which is 9.25. And so that's why we get a lower pH. And that makes sense because acid has low pH numbers. So the lower the pH, the more acid you have, right? So here, the pH is lower, so that fits nicely with the ratio of acid to base. And again, just to point out, if we add equal amounts of acid and base together, then this ratio would be 1. If you take the log of 1, you get 0, and so then the pH would be equal to the pKa at that point. Okay. Well, that's it for this video. I hope you enjoyed this video. I hope you learned something from this video. If you like this video, then please, by all means, hit the like button. Also, subscribe to my channel. If you do, click the notification bell up there and click all so you'll be notified by all the videos I put out. And finally, put a comment down below in the comments section, right down there, and let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me, and have a great day.